Here we are again.
Yes, join us, everybody. Join us August 14th at 19:30 Eastern Standard Time with Bob Ingram, Chief Bob Ingram of the FDNY Hazmat Operations for the After Action podcast.
Yeah. Like once again, Facebook, YouTube, comments are on. Bring your A game, talk to him. It's all free, and come on in and check it out. We also have Battery Destroyers Club episode 3 in the works, and we'll be burning some Teslas up in the Chicago area.
Yeah, and if you're tired of people throwing stuff at you because you're walking down the street topless, would I highly recommend going to the swag store and buying that shirt and many other more. They are going fast.
Yeah. So good stuff. And conferences we still got coming up. We have Continuing Challenge, Label Master Dangerous Goods Symposium, which is a first for us. It's a little bit more of an industrial side, but hey, man, I'm down.
But these are the guys. These are the guys that are producing a pellet-like or granular substance to help combat the lithium-ion batteries. And from what we can see and tell and play with, it actually does what it's supposed to. So we're really excited to go and be a part of this.
Yeah, so we're going to check out with those guys. We have the Virginia Hazmat Conference, Hot Zone, and the CBR&E Convergence, which we're going to be judges for a whole event. And I'm looking forward to that one.
Yes, fail.
Yeah, you all suck.
We're going to sit there like Caesar with thumbs up and thumbs down and just, that's what I'm hoping anyway.
We should get one of those wreath hats.
Yes.
Those like sweatband. But ours should be sweatbands. Because it's Florida.
Sweatbands with leaves.
The leaves are
embroidered in them. Yes.
Oh, you know what? I'm writing it down right now. We got to get those sweatbands.
Oh, do we get to wear like a toga robe?
Yeah, that's exactly how we're going to do this.
This is going to be beautiful.
Just don't tell anybody. Oh, shit. Right.
Yeah. Brian from Oregon's going to poo himself.
He's going to be like, no.
All right. That's not what we intended.
I hope you're back for the second part of Helium. I'm kind of enjoying this episode.
I am too. I know it's outside of our normal like response and things like that, but we're going to be touching on some stuff in this episode, and if we have to go into another episode, we will too. That will kind of touch on response a little bit, but I think it's important to understand, more about the products that we do. The more we can learn about it, the more familiar we are with it, the better we're going to be able to operate.
Yeah. So let's talk about, as we left off last week with what happens if we have shortages, right? If those things, like we said last week, MRI machines, right? Helium is critical for cooling the superconducting magnets of MRI machines. And a shortage can lead to increased costs for hospitals and clinics, including potentially limiting patient access to MRI services. What is that meter? ORTEC.
ORTEC. I think that was nitrogen.
Was it? I thought it was helium.
I think the ORTEC worked off of cooling nitrogen.
Yeah, there's a meter out there. I'm going to bet most of you have never even heard of this, but there was a meter called the ORTEC meter. It's currently in use, but it is a super duper high-end radiation detector, and it used something.
Right. It was either helium or nitrogen to keep it cold. In fact, it took like 2 hours to cool down.
Yeah.
Which is why it stayed in the firehouse, because, they don't like it when radiation runs came in a few minutes before the overtime kicked in, and we were just sitting there on scene going, just waiting for it to warm up, Chief.
Yeah, or cool down, actually.
Or cool down. Yeah, that's a valid point. And of course, right, those delays are going to create operational issues because people can't schedule it. They can't have available MRI services.
Yeah, and as you can imagine, again, in semiconductor manufacturing, we're using this helium to manufacture semiconductors for cooling and a protective gas during processes like plasma etching. And if anybody's a welder or a MIG welder, you know that we put this gas, usually like argon, to protect that the point where it welds, and it makes a much better connection. Well, in semiconductor, they use helium as that protective gas. So this shortage can disrupt the production, increase costs, and slow down all that stuff coming out of wherever it is.
See, I see us telling this to like our teenage girls and them looking at us being like, who cares? right? Like, how does this affect me? Well, the fact that you may want a new iPhone every 6 months, it could have an effect on you because the downstream, which is the consumer, can lead to shortages and higher prices in consumer electronics, including your cell phone, computers, and other gadgets and gizmos.
And then we talk about scientific research like cryogenics. It's essential for various applications such as particle accelerators, superconducting magnets, and low temperature physics experiments. These shortages could have a problem with that.
Yeah, the scarcity of helium can also impact the availability of liquid helium for cooling sensitive instruments, potentially affecting experimental results and leading to higher operational costs for things like laboratories.
We can have rocket problems like going into space because we use this to pressurize fuel tanks and purge fuel lines and rockets. I would think you could probably use something else too, but who knows? Shortages can disrupt that.
I bet you the helium is used because it's so light.
Reactive. Yeah, I'm in that too.
It's really, really light. So, but I don't know, man. If we have a shortage here on Earth, sending it into space may not be the best solution.
A little known fact is they don't really use jet fuel to get out. They just fill it up with helium and they float it right out in space.
It just floats up. It's slow. That's why it's so slow coming off of the launch pad.
Yeah. That's exactly.
And the fire that's generated, those are the same fake images.
That's just lights.
Yeah, they're the fake images. The same people that produce the round Earth to make us think that the world is round. Yeah. It's the same people produce the fire.
Yeah.
Satellite manufacturing is one of those downstream components that could be affected. And satellites, we literally just use literally. I haven't used it in so long. I was so proud of myself. We use satellite components in everyday life. Everything we do is run off of satellites. So if we have a difficult time getting satellites up, that's going to have a major impact on our everyday life.
Even welding, right? Welding, I said this before, helium is actually used as a shielding gas in certain types, and specifically gas tungsten arc welding, or GTAW, uses this. So this would affect costs, etc.
Yeah, which is going to potentially compromise the integrity of welded structures. And if you're living in a building that's, greater than 3 stories, you want to be careful with welded structures.
We also use helium for leak detection because it has inert properties and a very small atomic size. So industries such as automotive, refrigeration, air conditioning rely on this.
Yeah, so think about it. If they can't get helium, if they can't produce the specialized manufacturing processes for this, where this inert property is needed, that's going to create shortages on goods and services. And whenever there's a shortage, there's also an increase in production costs, which we end up having to pay for.
We can cut the next 2 out, but the balloons. What about the kids?
Well, what are they going to do without balloons that float to the ceiling? Because there's nothing sadder than balloons that are hanging they're just flaccid and chilling on the ground. It's not good. It's not good.
All right, take me to solutions.
All right, solutions for this. Right off the bat, conservation. Using helium more effectively and avoid wasting. Now, I don't know if changing your voice is considered wasting. I don't. I find that to be a valuable part of any birthday party. So, but in other ways, we can learn to conserve and use less.
Or substitute it. Maybe we can use hydrogen instead.
Recycling, right? We said before that it's there. It's not a commercially viable, but if we can invest a little bit of money and figure out ways of developing new technologies that would be able to capture and reuse the helium, that might be a good thing.
Or even just start drilling and bringing up more natural gas, which is a huge potential source of helium. But now we have to store it, right? We got it and we have it. And so how can we restore it? Well, we could do it through a compressed gas cylinder is one.
Helium is often stored in high pressure cylinders made of steel or aluminum.
Right. And these cylinders can be easily transported and used in various applications.
Like so many other gases, right? We get a very economical way of storing helium by cryogenically liquefying it. And we know that helium can be cooled to very low temperatures and stored in a liquid inside an insulated containers that we would call a dewar.
Right, which is how we're using this in MRI machines and scientific research.
Yeah, and the cryogenic cooling process is actually pretty cool, right? We want to take and lower the boiling point. Helium has the lowest boiling point of any element out there, so it's excellent for cooling and achieving extremely low temperatures. And we use those for things like MRI magnets.
Right. Which in those things, we need supercritical temperatures where they exhibit like basically zero resistance electrically. And that's
just crazy to me.
And helium has the ability to reach those temperatures and ensures those magnets remain in that superconductive state, allowing them to generate strong, stable magnetic fields needed for the imaging. You want the 4K? You got to bring the helium.
So how about how does it change the efficiency and the performance, right? By the high conductivity, helium has the ability to absorb a tremendous amount of energy, which means it has a high thermal conductivity, right? We're just interchanging words. So if you're doing research and you see these things, that's what it means. It can effectively transfer heat away from those superconducting coils, helping to maintain those low temperatures during operations.
Right. Which means you have increased efficiency, right? If you have helium cooling the MRIs, they can run
stronger. It's like a gas Viagra. Right. Think of it like that. And one of the last things that it does is it enhances the quality of the image, right? If you have a strong magnetic field, then you are going to get a more stable picture. You get better resolution in your quality, and all of that resolution and that fine detail is absolutely critical for accurate medical diagnoses.
Okay, so let's go into storage. We have a lot of it in underground storage reservoirs.
And we can extract a pretty decent amount from industry. So how
the cost of this storing helium, especially as a liquid, can be expensive due to the need for those specialized equipments.
Yeah. So there is an infrastructure issue with that as well, because it requires very specialized infrastructure for both the storage and the transportation. Now, that special infrastructure comes because there are some engineering issues when you're dealing with one of the smallest elements known to humanity. Because helium is so small, you have permeability issues, right? This is one of the first engineering problems that has to overcome. The tininess of helium allows it to permeate through many materials, which we would consider to be otherwise impermeable to anything else. So a high quality material and precision engineering are necessary to contain the helium effectively.
Right. So they typically use like stainless steel or aluminum. Now, imagine this. Let's say you had a absolutely perfectly done.
So
no gaskets, no valves, no threads, no nothing, stainless steel or aluminum. It would often allow aluminum to go through it because the helium goes through the metal.
Yeah, like between the metal atoms, the space between the metal atoms, it just kind of travels through. So how crazy?
It is crazy.
That is crazy, right? I mean, I know hydrogen does the same thing, right? There's the same issue with hydrogen, but that just seems crazy to me. What about blowing a seal? So right? Like you always have to ensure airtight seals in containers. It's a critical aspect of keeping something inside the container. Traditional sealing methods may not be effective. It requires specialized techniques such as an indium gasket or other high-performance sealing materials.
Yeah, and when you have this thing in a cryogenic space, right, we're talking, I mean, like 4K, like 4 Kelvin is where this thing hangs out. You're requiring very different things because things don't react well in at 4K. So you're talking about specific materials that can handle such conditions without becoming brittle or losing the functionality.
Yeah, I mean for cryogenic stuff, the container interactions are absolutely insane. I mean, think about that. The thermal expansion and contraction alone of helium containers, especially when they're in that kind of cryogenic form, can be a massive stress on the material, a massive stress on the seals, and the engineering has to overcome that potential for leaks and structural failure.
And because of that expansion ratio, or because of that, the cryogenic management of the cryogenic property of it, it's often stored under high pressure, which means like as it expands, it really wants to expand. It pressurizes, it gets big. And so you have pressure problems. Expand. Pressure. Right now, when I have it coming out, I have a real problem with asphyxiation. It's an inert gas. It displaces oxygen in air. In confined space, helium leaks can create an asphyxiation hazard, especially with making people unconscious. Now, luckily, I don't belong to the helium family. So when I'm standing on the ground, the air is up there. Now, expand. Again, keep in mind, if my nose was on my foot, it would be better for me helium-wise.
Yes.
But because my nose is on my face, my head is higher, and helium is more of a problem.
So really, it all depends on your ceiling.
Expand, pretty much. The higher the ceiling, no problems.
Less the problems. There is an explosion risk.
What?
But wait, fat man, you just said it doesn't react. And in order to have an explosion, you have to have fire and No, helium is non-flammable. But these high-pressure containers have the ability to fail, and we would consider that to be an explosion because of the massive amount of energy that would be released during one of these high-pressure failure events. Proper pressure relief devices and regular maintenance are critical to preventing catastrophic failures.
Right. And again, because it's so cold, you can have cold burns, which kind of is an oxymoron. But if you please don't touch cryogenics with your fire gloves. They're made for fire.
Not
cryo. Okay.
Right.
We have to worry about purity maintenances. Something like an application often needs high purity and no contaminants. So this is kind of like very pure stuff, but with that, your container must be designed to hold that purity over time.
Yeah, the storage efficiency plays a role in all this stuff too, right? Like, why not just get a massive container of liquid hydrogen and just only take it when you need helium, and take it when you need it? Well, it's going to boil off in the cryogenic container. So if you're not using it a certain rate, then you're actually wasting more helium than you are using, and your storage efficiency goes way, way down.
Right. So you have some regulatories like DOT and OSHA. They have some stuff to say about it. We're not going to get into it. Go read it on your own.
Yeah.
All right. So we have to worry about some stuff here, right? We have some pressure issues.
Yep.
And we have some reactivity issues.
Yeah. So when it comes to compression, helium can be highly compressed. And when it's subject to those high compressions, which is something that would be found, say, like deep inside the planet or under high pressure experiments, the atoms can be forced really, really, really close together.
Let's finish this thing up with some PPE. We have to use some cryogenic stuff. You have cold. You need cryo gloves, face shields, insulated suits. Face shields are kind of important because this stuff gets angry when it hits a hot surface. And considering that just about everything is hotter than 4 Kelvin,
usually
it's going to spit at you. Yeah.
A respiratory protection, right? We know it's an asphyxiation hazard, oxygen displacement. So we should always be wearing respiratory protection anytime we're working in, around, or even the potential that we could do something that could cause a massive helium leak.
Right. And obviously, thickness of your clothing counts. Have some insulation.
Yeah. So doing site assessments and isolation are definitely some things that we can do when we get on scene. Your initial assessment is going to be what is the leak? What is the potential hazard? How bad is the leak? And do I definitely have helium gas or do I have helium liquid? And what is the rate of release?
Right. And just with that, evacuate as needed.
Yeah. What is your isolation zone? Probably, honestly, pretty goddamn small because helium goes straight up into the air. So if this is outside, you really don't have an isolation zone. What our isolation zone would be considered for is if we were going to have a pressure event.
Right. And obviously, we're going to vent. If we have a problem, you vent the area. Open fans, start fans, open doors, open windows, enhance the flow.
Now, oxygen meters and regular meters you're dealing with a very small molecule that may have some weird interactions with different technologies. But we do, to the best of our ability, want to monitor for oxygen levels using portable gas detection. If you're on air, do we really need to do it? Well, it's nice to know the extent of the leak. And just as an FYI, helium can produce a reading on your CGI.
Well, with that, if we have a leak, we want to determine where it is, like the valve failure or container rupture or whatever it is. And when I said ventilate, obviously we're going to vent the upstairs.
Right. As high as possible. As high as possible. Now, stopping the leak. Do we want to stop the leak? I don't know if stopping the leak is always the best bet when it comes to something like helium. If you're going to do so, you should understand what the ramifications of stopping that leak or closing that valve or sealing that material is going to do. If you can't predict the behavior is safer than the leak, then don't stop the leak. Right. In my opinion.
Right. Now, let's take care of the mitigation and take this home.
Yeah. So cold burns, right? That's one of the things that we have to worry about the most. We kind of covered that in PPE. Understand that these surfaces are going to be cold, and it's not just the liquid that's going to be cold, but anything that this liquid touches and boils off of is going to take on some extremely cold temperatures and change the behavior of the material that it's boiling off of.
And just one thing to finish this up is that, pressure with it being cryo, typically, you have pressure release. So if you're going to close valves, know what valves you're closing, because if you box the cryo in between two valves and it naturally starts heating up, pressure is going to build in that. So helium is a weird one. Hope you're done with it now.